The parts present in this unit are like core of embedded system, which are general purpose and domain specific processors, ASICs, PLDs, commercial off-the-shelf components, different memories, ROM, RAM, memory according to the type of interface, memory shadowing, memory selection for embedded systems, and along with that, sensors and actuators, communication interface devices will be seeing in this second unit. This is the broad representation of embedded system along with core, I/O parts, different other parts connected to the system. In the center, that is representing a system core. The system core could be FPGA, ASIC, or DSP or system on a chip, or also microprocessor or a controller. Based on the application, user can select either a large component that is FPGA or a small component that is controller. Different embedded systems will have different core processors. A simple toy, if you consider, it may consist of controller. If it is an application like system on a chip, or if it is an application related to a big complex functionality, then a system on a chip or FPGA can be selected. That is about core. Now for the core, input-output devices are connected. Input ports are connected with sensors. Various sensors like a temperature sensor or humidity sensor or any other sensor will be connected as input device. The entire input devices comes under input ports. Most of the embedded applications uses sensors as input devices. Similarly, for the output devices, based on the input signal, output devices could be either actuators. Actuators also similar to sensors. They will take the information from sensors and accordingly they will generate an output. Then output ports are like some relays or LCD displays or any other components. Along with these I/O devices, the core will be connected to a memory. That memory is for storing of information permanently, like a ROM memory, or user interfacing device data like a RAM memory. So this is permanently stored memory, also represented as embedded firmware, that will be stored in ROM, or user interactive information that will be stored in RAM. Different memories will be connected to the core of the system. Then other parts are like communication interfaces, network adapters, and all connected can be connected to the core. And other supporting devices that are integrated circuits or subsystems can be connected to embedded system. The whole system is called as embedded system. Now the core of the system consists of like general purpose and domain specific processors, microprocessors, microcontrollers, and special processors like digital signal processors for communication applications. Then application specific integrated circuits, shortly ASICs, programmable logic devices, PLDs, and the commercial off-the-shelf components. These are considered as core of the embedded system. Based on the application, users or designers can select one of the cores. Then, in terms of microprocessor, microcontroller, generally when the designer considers either of microprocessor, microcontroller based on the application as well as the differences. Let us see a few differences between microprocessor and microcontroller. As we are seeing, this microprocessor is a silicon chip represented as a central processing unit, and this requires combination of other hardware like memory, timer, interrupt controller, and all these hardware required for proper functioning. Whereas microcontroller, it is highly integrated chip that contains the CPU, scratchpad RAM, special and general purpose register arrays on the chip itself, along with memory ROM, flash memory, and these are all required for program storage as well as timer, interrupt controller units, and dedicated I/O ports. All these comes within the chip itself, that is microcontroller. Now, under microprocessor, we can see another difference is it is time dependent unit, and then it is dependent on unit. It is a dependent unit requires combination of others like timers, program and data memory chips, interrupt controllers, etc. for functioning. Whereas here it is self-contained unit. It does not require external interrupt controller or timer or UART. Everything is placed in the chip itself for its functioning. And most of the time microprocessors are general purpose in the design as well as operation, but here microcontrollers are for specific application. And the microprocessors are targeted for high-end market where performance is important, whereas microcontrollers are targeted for embedded market where performance is not so critical. But the important is compact and less number of components to be used, as well as fast in operation. All these under embedded design constraints. Then limited power saving options compared to microcontrollers, whereas microcontroller power saving features are many because these are using less number of devices. Similarly, all the components are within the chip itself is available, so power dissipation is almost reduced compared to microprocessor. Once the microprocessor and microcontrollers are identified, again we have to observe what type of architecture they are built up. The embedded system especially takes either microcontroller or microprocessor, again based on the complexity of the processor. The complexity of the processor is mainly depends on the architecture. So there are two types of architectures, Harvard as well as von Neumann architecture. So if you see the differences, Harvard architecture uses separate buses for instructions as well as data, and this follows the pipeline. So high performance is present, and Harvard architecture is comparatively costly, and data and program memory are stored physically in different locations. So there is no chance of existing accidental corruption of program memory. But in the case of von Neumann, it shares a single common bus for both instructions as well as data. And because of this low performance as compared to Harvard architecture, and since a single memory structure, it is cheaper, and there is chance of accidental corruption of program memory and data because it is available in the same space only. So these are few differences. Then let us see DSP processors. This is also a part of core. DSP processors are powerful special purpose 8 or 16 or 32 bit microprocessor designed to meet the computational demands and power constraints of today's embedded audio, video, and communication applications. And because of the architectural differences between DSP and general purpose microprocessors, DSPs are 2 to 3 times faster than general purpose microprocessors. And then DSPs can be found more in signal processing applications. DSPs are implementing algorithms in hardware which speeds up the execution, whereas general purpose processors implementing the algorithm in software. And the speed of execution depends on primarily on the clock for the processors. That is one major difference. Then DSP processors generally use program memory. It is meant for storing the program or program data, and other memory is data memory. The main purpose of this data memory is storing temporary variables, that is the data or signals to be processed. It is also named as working memory. The other component that uses the DSP processors is computation engine. This computation engine is nothing but a collection of arithmetic units, similarly hardware shifters, and many other small components come together as the computation engine. Then the processors also can be categorized into RISC as well as CISC processors. That depends on embedded application. So designer can choose either RISC processor for simple constructions or simple functional designs, or else they may select the CISC processors for complex functional designs. So as the name suggested, RISC is reduced instruction set computer, whereas CISC is a complex instruction set computer. So RISC consists of less number of instructions. That's why the name also mentioned as RISC, reduced instruction set computer. Whereas CISC have complex number of instructions or greater number of instructions. Then because of simpler instructions, the RISC allows us for pipelining and increased execution speed. Whereas CISC pipelining is difficult, generally difficult. because most of the instructions are represented like a macros. So each execution of each instruction takes several times of number of instructions. So pipelining is a little bit difficult in case of system. And as well as orthogonal instruction set, nothing but each instruction to operate on any register and use of any addressing mode. That facility is present in this processor, whereas in the case of CISC, such facility is not there. Non-orthogonal set, all instructions are not allowed to operate on any register. So each instruction has its relevant register. Each instruction has its specific register to be used. So that is one major constraint under system. Similarly, in RISC, operations are performed on registers only, or only memory operations are load and store. We can observe that only load and store operations in RISC. Whereas in the case of CISC, operations are performed either on registers or on memory, depending on instruction type. That flexibility is there. Then a large number of registers are available in RISC, whereas very few registers are available in CISC. That is general purpose registers we are talking about. Then programmer needs to write more code to execute a task. That is one drawback with RISC. Whereas here instructions are available like macros in C language. So very few lines of code is sufficient to perform any task. So less number of lines of code is sufficient for system. Then it is a single pixel length instruction, whereas here instructions are variable length. As we are seeing in microprocessor 8086, like variable length, it can be available 1 byte or 2 byte or 4 byte instructions like that. Variable length instructions can be available for CISC processor. Then two more differences are like less silicon usage and pin count in RISC processor, whereas more silicon usage in CISC processor, because it requires a lot of decoding process, because each instruction is represented like a macro. That decoding of macro requires a lot of logic, so it uses more silicon area. And this will be used with a Harvard architecture, whereas CISC will be used with Harvard or Van Neumann architecture. And these are few differences between RISC and CISC processors. Then let us see application specific integrated chip. This is also used as a core of the embedded system, ASIC, application specific. ASIC is a microchip, actually this design to perform a specific and unique application. And because of using single chip for integrate several functions, it reduces the system development cost. And most of the IPs are nothing but ASICs are proprietary products. Proprietary products, nothing but it is referred as the application specific standard products, ASSP. Then as a single chip, ASIC consumes a very small area in the total system. That is one advantage. Thereby helps in the design of smaller systems with high capabilities of functionalities. So this is application specific integrated circuits. Most of the time, embedded systems uses a special kind of ICs. That means they are meant for a particular operation. So ASICs will take development of small systems, means less time, and it will be easy to implement also. So ASICs will have its own advantages. Now, core processors can also be PLD, CPLD, or FPGA. So PLDs are like electronic component. It is used to build a digital circuits which are reconfigurable. A logic data has a fixed function of PLD does not. A logic gate has a fixed function, but PLD does not have a definite function at the time of manufacture. Only after programming we can observe that PLDs are defined with the logic function. Then PLDs offers customers a wide range of logic capacity, features, speed, voltage characteristics. PLDs can be reconfigured to perform any number of functions at any time. That is another advantage. PLDs do not require long lead times for prototypes or production parts because PLDs are already on a distributor's shelf and ready for shipment. And PLDs can be reprogrammed even after piece of equipment is shipped to a customer. That is another advantage. Varieties of tools are available for the design of PLDs, which are inexpensive and help to develop, simulate and test the designs. And FPGA CPLDs are two major types of PLDs. That CPLD is complex programmable logic device, sorry. And the CPLDs offer much smaller amount of logic, that is up to 1000 gates, whereas FPGAs are field programmable gate arrays. They are more complex compared to CPLD and also have highest logic density and more features compared to CPLDs. And what are the advantages of PLDs if we see? PLDs offer customer much more flexibility during the design cycle. That is one advantage. And they do not require long lead times for prototypes of the production parts, because of PLDs are already on distributor shelf and ready for shipment. So PLDs can be reprogrammed even after piece of equipment that is shipped to a customer. That is advantage of PLDs. Now, one more is cost, that is commercial off the shelf is also can be used as core part. This one is actually strictly speaking, it is defined as the shelf product. Commercial off the shelf product is one which is used as is. As is the term, that is that as it is how available, like that we can use in the applications. So cost component itself may be developed around a general purpose or domain specific processor or an ASIC for PLDs. That means what are the existing development is there, as it is we can take and we can develop something above that on the existing one. Like an example, like TCP/IP plug-in module, remote control of a toy car or TV remote. All these like from the existing components that will be developed, and moreover, once the design is meant for a particular design, that will be lasting for with that only. So further upgradation may not be seen in this. That is a disadvantage. Advantages are ready to use, easy to integrate, reduces development time. But disadvantages of cost are no operational or manufacturing standards, all proprietary. That depends on designer wish. And vendor or manufacturer may discontinue production of a particular cost product. For example, earlier versions of Nokia that was upgraded, but that first version of Nokia phone now it is not available. Similarly, for cars, if you take as an example, some types of cars, some car models are not available. So like that, production may be stopped anytime. That depends upon the designer wish, vendor or manufacturer wish. So cars are nothing but the development from the existing components. Now let us see, as till now we have seen core parts of embedded system. Let us see the discussion on the other components like memories. So there are various types of memories that are supposed to be used in embedded system. They are like ROM, RAM, hybrid memory. Again, types of RAMs we can see in the future slides. So basically, what is RAM, ROM? RAM is random access memory. It is a read memory. It's also called as read memory, random access memory or read memory. It is volatile memory. Data access to memory is very fast in this case, right? Data can be accessed at any location to read or written. It is a volatile memory also. It retains the content as long as electricity is supplied. And coming to the ROM, it is read-only memory. That means once the data is present, only we can access the ROM for reading. We cannot write into that. Data at any memory location can be only read. It is a non-volatile memory, that is contents are retained even after electricity is switched off and available after it is switched on. And one more difference is data access to ROM is slow compared to RAM. One more category, that is hybrid. Hybrid is combination of both RAM and ROM. It is that means the characteristics of RAM available as well as ROM available in this, right? And it has certain features of RAM and some of the ROM. Like RAM, it contains to hybrid memory can be read and written, but like a ROM, the contents of hybrid memory are non-volatile. So having the two features, we can name this memory as hybrid memory. Now this is a small flow diagram like memory. This is the first one, and it is categorized into RAM, hybrid and ROM. RAM is again further categorized into DRAM and SRAM. Hybrid is again categorized into NVRAM, flash and EEPROM, and ROM is categorized into EPROM, PROM, and masked ROM. Let us see. Let us see one by one what is this one. So types of RAMs are SRAM and DRAM, static RAM and dynamic RAM. Now generally this static RAM is retains the contents as long as the power is supplied to the chip. That's why not only that, static RAM uses 6 transistors, and in which 4 transistor core, that is what are the 4 transistors we are using as a core, like 2 inverters are connected back to back. They are meant for reinforcing the data which is written. So because of the reinforcement, the data will be present till the data is taken out in terms of read operation. So when you read data without violation, what is the data you have written? That is only will be read again. So that's why static RAM, the name is given so. And if the power is turned off, the contents will be lost in both SRAM and DRAM. It's not because of power. It's not because both SRAM and DRAMs are volatile only. Only static is meant for because of the data reinforcement, exact data will be read out. Then dynamic RAM is short data lifetime because it uses a capacitor and one transistor. Because of the capacitance, what is the data you write, that will be because of the capacitor that loses its data a little bit. So what is the data you wanted to read may not be a perfect logic or a logic the data which you have written. That is why periodically it requires a refreshment of the data stored in the DRAM. By refreshing the data several times a second, the DRAM controller keeps the contents of memory alive for a long time. So that is the major difference between SRAM and DRAM. One more is masked ROM. So under ROM, masked ROM, PROM, EPROM categories can be seen. Masked ROM is a hardwired memory device. It contains pre-programmed set of instructions and data, and it cannot be modified or appended in any way. It is just like an audio CD that contains the songs pre-written on it and does not allow to write any other data. That is the masked ROM, and the main advantage of masked ROM is that is low cost production. Then second one is PROM, programmable ROM. These are also known as one-time programmable OTP devices because any data can be written it only once. Then it cannot be modified. If the data on the chip has some error and needs to be modified, then entire chip has to be modified because it is one-time programmable. Now coming to EPROM, erasable and programmable ROM. So it is also similar to PROM, programmable read-only memory, but it can be erased and reprogrammed repeatedly as the name suggests. The ease of operation in case of EPROM is performed by exposing the chip to a source of ultraviolet light. That is the main advantage. Reprogrammable ability makes EPROM as essential part of software development and testing process. Now coming to other types of memories, that is hybrid memory, EEPROMs, electronically erasable programmable ROM. So that electrically erasable and programmable ROM, it is same as EPROM, but the erase operation is performed electrically. Any byte in EEPROM can be erased and rewritten as desired. And second type of hybrid memory is flash memory. These devices are high density, low cost, non-volatile, fast, that is to read but not to write, and electrically reprogrammable. And another category of hybrid memory is NVRAM, non-volatile RAM. Generally, RAM itself is volatile, but this NVRAM is non-volatile RAM, is usually just SRAM with battery backup. When power is turned on, the NVRAM operates just like any other SRAM. But when power is off, NVRAM draws enough electrical power from the battery to retain its content. NVRAM is fairly common in embedded systems, and it is more expensive than SRAM, we can observe. And the main drawback in terms of memory, that is memory shadowing. Memory shadowing is it will take a little bit time to boot up from the data which is taken from ROM. So this is a technique that is probably best known from its implementation with the BIOS ROM used in a PC. The idea behind shadowing is to copy the contents of the slow ROM into faster RAM and execute the code from the RAM. As a result, time taken to execute the code is greatly reduced. The shadowing refers to the fact that the RAM contains a copy of the original RAM contents. The mechanisms can be implemented either with hardware assist or entirely in software. The basic principle behind the hardware assisted implementation is the address decode logic is used to switch the address decode to select the RAM instead of ROM. And whereas second technique is software based implementation. In this software that is copied is now in different memory location, and providing the software was compiled and linked to execute in this location. So using these two mechanisms, we can eliminate the memory shadowing problem. Now these are other components which are connected to the core processor, that is sensors and actuators. A sensor is a device that is used for taking the input. It is a transducer that converts energy from one form to another form for a measurement or for control purpose. Whereas examples are temperature sensor or humidity sensor. The other component is actuator. It is used for output device. It is a transducer that may be either mechanical or electrical, which converts the signals to corresponding physical actions. Examples are LED or LCD, any others. Then let us see communication interfaces. These are used for internal communication of the embedded system, that is communication between different components present on the system. So common examples are onboard interfaces, that are IIC, inter-integrated circuit, serial peripheral interfaces, PI, universal asynchronous receiver transmitter, UART, one-wire interface, parallel interface. And external or peripheral communication interfaces are RS-232C, RS-485, universal serial bus, IEEE 3094 firewire, infrared, IRDA, Bluetooth, Wi-Fi, Zigbee, general packet radio service, GPRS. And more into this one, the information you can go through from the handouts which are present in our Moodle. So here with this I can stop the presentation, and this is all about Unit 2. And in this Unit 2 we have seen the core of the embedded system along with the other parts connected to the core. So with this we can wind up the presentation. We will see in the next presentation for third unit. Thank you all.